Chapter 3 is called Applications of Differentiation. We're going to be applying derivatives. Now, this first section is called Extrema on an interval. Extrema means extreme values. Extreme values, maximums and minimums values. Okay? So on page 164, we have our definition of extrema. It says, let f be defined on an interval containing the x-coordinate c. First, f of c. So f of c means the y value, the value of the function. The y value of the function is the minimum of f on that interval if that y value is less than or equal to all the other y values in the interval. It does make sense. One of the few things that ought to fairly intuitively make sense. The smallest y value on an interval is called the minimum. Okay? Part 2, f of c, that's a y value, is the maximum of the function on that interval if f of c, that particular y value, is greater than or equal to all the other y values on the interval. So the minimum is the least y value, the maximum is the greatest y value. Okay? Make sense? All right, now, some vocabulary. The minimum and maximum of a function on an interval are the extreme values, or extrema. The singular form of extrema is extremum of the function on the interval. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum on the interval. Now, why would we throw in an extra word there, absolute? Because in a few minutes, well, later we're going to have relative maximum and relative minimum. Okay? So, you with me so far on extreme values? All right. The extreme value theorem, which is still on page 164, says if f is continuous on a closed interval, and remember on a closed interval, the endpoints are included. Okay? So, A and B are included in the interval, which means f of A and f of B are values in that interval. Then f has both a minimum and a maximum on the interval. And let's look and see how this works out. So the first figure here is an example of where this theorem applies. Okay, now how do I know if a theorem is going to apply or not? If the hypothesis is met. So the hypothesis is f is continuous on a closed interval from A to B. So look at the first graph, this one. F really is continuous on that closed interval from A to B. So according to the theorem, the conclusion must be true that f has both a minimum and a maximum. Well, it does. The minimum is 1, the maximum is 5. Notice that one of those extreme values occurred at the end point. Now, that won't always be true, but you need to realize you may have a maximum value simply because you reached the end. Okay? Because if we didn't have this end, the function might keep going if the interval kept going, but the interval stops. So the function stops. So you might have an extreme value at an end point. If the function is a horizontal line, three is the maximum and 3 is the minimum. Greater than or equal to. Okay? So, see, I mean, that's where you got to be careful when you make a definition. And I'm sure that way back when they first made the definition, they probably didn't put the or equal to on there. And then they realized that things like this didn't work unless they put the or equal to on there. Okay? All right, does that make sense? Now look at this next figure. The theorem does not apply to this next figure because the hypothesis says f is continuous on the closed interval from a to b. This function doesn't exist at x equals a or at x equals b, so the theorem does not apply. Now you might say, but it works anyway. Well, almost. How come they've written out here not a maximum? Right, because you might say, well, 4.9 is the maximum. Well, then we play this game. No, it's not. It's 4.99. Then you say, no, it's not. It's 4.999. Right? You never get to 5. 5 would be the limit, but you never get there. We could say, well, what's the limit as x approaches 2? And it would be 5. Okay? But see, but we're never getting a number. Okay? All right, and this last graph, this function does exist at the endpoints, but then it's not continuous right there. So it does have a maximum at one of those endpoints, but not a minimum, because same idea, it's going to keep getting closer to 1, but it's never going to exactly equal 1, so there's not a number that we can point to and say that's the minimum value. All right, so far so good? Now notice on the one here where it did apply, one of our extreme values was at an endpoint, and thinking about a derivative for a minute, what would the derivative be where that other extreme value was? What would the derivative equal right there? It'd be 0, wouldn't it? That'd be a horizontal tangent line. Keep that in mind. Sometimes we get extreme values at an endpoint of a closed interval. Sometimes we get extreme values where the derivative equals 0. All right, definition of relative extrema. All right, so we did get to it in a few minutes, didn't we? If there is an open interval containing C on which f of C is a maximum. Now look what they've done here. They've changed the wording. Open interval. So now we don't have to worry about endpoints on this, do we? Okay? Because the endpoints don't come into play because they made it an open interval. Endpoints are not in an open interval. So if there's an open interval on which C, containing C, on which f of C is a maximum. So that's the y coordinate that's a maximum. It's greater than or equal to all the other y coordinates in the interval. Then f of C is called a relative maximum, or you can say that f has a relative maximum at the point C, f of C. Now they've changed from absolute, first they said maximum, then we said absolute maximum, now we're saying relative. Here's the difference. Anita, if I've got a function that does this, whatever this y coordinate is right there, that's a relative maximum because it's larger than all the y coordinates in a reasonable interval around it, isn't it? But it's not the maximum because when we go over here, to the right part of this graph, these y coordinates over here are greater than that y coordinate I called a relative maximum, aren't they? Okay? So relative means relative. Relative to all the y coordinates in the interval near it, it is larger, it is greater, therefore it's a relative maximum. So when we don't have a closed interval, do I want to say rarely? I'm going to go for it. When we don't have a closed interval, we rarely have an absolute maximum and minimum. Sometimes we do. It depends on what the graph looks like. With a closed interval, you will find an absolute maximum and an absolute minimum. Without a closed interval, so with an open interval, you may only have a relative maximum or minimum. Either. Yep. Like, for instance, there just wouldn't be, well, let's do this. Let's say that we have the open interval from A to B, open. So we'd be talking about this part of the graph. There is a relative max. We'll talk about you a lot for a while here, Max. There is a relative max right there at f of c. But there's not anything that we can call a minimum, whether we qualify it as relative or not, because, you know, as the x-coordinate moves closer and closer to A, it keeps getting smaller, but there's never a smallest number. And as the x-coordinate moves closer and closer to B, it keeps getting smaller, but there's not a smallest number. All right, so see, this theorem doesn't apply because it's not a closed interval. That theorem only applies to a closed interval. So with an open interval, you may not have a max or a min, or you might have one, not the other. You might have both. They'll be relative, okay? Yeah. Do you have a question? No?
Basically, like, if you move the right open circle all the way to the end of it, your relative max would still be in the position.
Yes. Yep. Yep. If we erased this little open circle and moved it to here, let's say. So this is the function and the interval we're talking about. With what we've already identified as a relative max is still a relative max. And then right here, at whatever that x-coordinate is, E, would be a relative min. And as you can see, we say max and min a lot because you get tired of saying maximum and minimum.
So the principle of like it being relative is because there's a circle there that would otherwise be maximum. Why you say relative?
Well, let's go back to here. This one right here is a relative minimum and an absolute minimum. As long as you're, I'm not sure how to define this. I know that as long as your relative max or relative min is not at an end point, it might also be absolute. Now this would be the absolute maximum. I'd have to relook at the definition and think about it for a minute to know if we could also call that relative maximum. I think anytime it's absolute, you can also call it relative. Yeah. I don't know. I'd have to think about that to be sure. I'm not sure you can. I'd have to look at it and stop and think. Okay?
When open interval, the open circles, they were maximum and minimums, like they were kind of in the middle of the Y range.
Like if we had there and there.
Well, if you had the first one.
If I had this one and this one.
Well, you got 3.
This one and this one.
Like, the two would cross each other if
The
you had
left
those
one.
two at the
The left
All right. Let me redraw this. I've got this.
bottom right green,
Where do you want the open circles?
left side. First one.
There? Okay. Where do you want the other one?
The bottom right.
There? No.
bottom right.
Yeah, the bottom right green.
There.
Yeah.
So
Okay.
it's okay. Like they're not going to get maximum or minimum anyway. Or the maximum and minimum is their relative or absolute.
Oh.
We call them relative. And then if we state an interval, then we can say absolute. So if we say from A to B, then yes, we can call them absolute. Okay? If we're going from negative infinity to infinity, they're relative. You asked the perfect question. I finally got what you're getting at. Does everybody get that? Okay, if we're just from A to B, we can call them absolute because that is absolutely the largest y-coordinate in that interval from A to B. This is absolutely the smallest y-coordinate in that interval from A to B. But if we're going from negative infinity to infinity, we've got to stick with relative maximum and relative minimum because, look, there are y-coordinates larger than this one. And there are y-coordinates over here smaller than the one we called a minimum. Hence the name. Okay? All right, I think we finally got it. I got it. You got it? Okay, we were here. We were here. All right, so then we do the same thing for minimum. So instead of going through it all again, just relative maximum, larger than all the y-coordinates in an interval nearby. Relative minimum, smaller than all the y-coordinates in an interval nearby. Relatives can also be absolutes. They don't have to be. Okay? You think you got it? All right, a couple things I want you to notice. Right here would be a relative maximum. What would the derivative equal right there? Right here is a relative minimum. What would the derivative equal right there? Could I possibly call those absolute extreme values? Only if I chopped off an interval, right? If I made the interval from like there to there, then yes, I can call them absolutes. If I go from negative infinity to infinity, can I call them absolutes? No. Charlie? Sounds good to me. Open interval can be anything as long as the endpoints aren't included. Okay? All right. Right here, where they point out a relative minimum in this graph right here, what would the derivative be right there? Doesn't exist. What's the derivative here at that relative maximum? What's the derivative here at this relative minimum? You starting to see a pattern? No? What's the derivative right there at that relative minimum? Right there at that relative minimum. At that relative minimum. At that relative maximum. At that relative and absolute maximum. Does not exist. At this relative and absolute minimum. Does not exist. So far with the graphs we've looked at, where have extrema occurred? They've occurred at the end point of a closed interval. They've occurred where the derivative equals 0. They've occurred where the derivative does not exist. Questions? All right. Now, we have a special name for these places where the derivative equals 0 or does not exist. I'm on page 166 now. Definition of a critical number. Let f be defined at c. So in other words, f of c does exist. All right, the function exists at this point. If f prime of c equals 0, or if f is not differentiable at c. So at c, the derivative equals 0 or the derivative does not exist. Then c is called a critical number of the function. So a critical number is an x-coordinate where the derivative equals 0 or the derivative does not exist. We will be talking critical numbers the rest of the year. So you need to know this. A critical number is an x-coordinate where the derivative equals 0 or the derivative does not exist. Now, like we've been talking about, if the derivative equals 0, it's a horizontal tangent line. If the derivative does not exist, it's a cusp. And this next theorem, which is also on page 166, is a biggie. Relative extrema occur only at critical numbers. If F has a relative minimum or relative maximum at C, then C is a critical number of F. Pay attention to the direction. It doesn't say that every critical number leads you to a maximum or a minimum. It says that every relative maximum or relative minimum occurs at a critical number. The order matters here.
So not every critical number is a relative minimum or relative.
Exactly. Not every critical number leads you to an extreme value. However, every extreme value comes from a critical number, with an exception. They can also occur at endpoints of closed intervals. Okay? So, which means, now that I've read this part, which means back up here, we can't call that a relative maximum. It doesn't fit our definition. We can call that one an absolute. So I was wrong about that. Absolutes aren't always relative. We can call that one absolute. We can't call it relative. So endpoints are an exception. It's kind of like in algebra when we were learning about lines, and vertical lines were always an exception to everything you learned about lines, right? Because their slope was undefined. You just got to remember endpoints of closed intervals, okay? So if there are not any endpoints, the only place a maximum or a minimum can occur is at a critical number. If there are endpoints, you got to check those too. Okay. And I rephrased that just a bit. All relative extrema occur when the derivative equals 0 or when the derivative does not exist. Okay? All relative extrema occur when the derivative equals 0 or when the derivative does not exist. And I think graphically we've seen that, haven't we? All right. Before we move on, are there any questions? Guess what we're getting ready to do? We're getting ready to find relative minimums and relative maximums, okay? All right, so on page 167, they give us some guidelines. To find the extrema, well, it's some guidelines for finding the extrema on a closed interval. So they're giving us endpoints. To find the extrema of a continuous function on a closed interval, use the following steps. Step 1, find the critical numbers of the function. Well, you know what they didn't even bother listing as a step? Finding the derivative. They're assuming you can find the derivative. Because you can't find critical numbers if you can't find the derivative, can you? Because what are critical numbers? They're where the derivative equals 0 or the derivative does not exist. So it's just assumed you're able to find the derivative. All right, so find the critical numbers, and let's say our interval's from 0 to 5, and we find out that the derivative equals 0 when x equals 12. 12 is not a critical number because it's not in the proper interval. Okay? So if they give you an interval, it matters. If they don't give you an interval, it's the domain of the function, usually negative infinity to infinity. Okay? Evaluate the function at each critical number. Evaluate the function at each endpoint. Because where can the extreme values occur? At critical numbers and at endpoints. So you find the value of the function at every critical number, at every endpoint. Then the least of these is the minimum. So you find the only places where the minimum can occur, and the smallest value you get from those places where the minimum might occur, that's the minimum. Then the greatest is the maximum. So we're checking the only places where the maximum can occur, right? Critical numbers and endpoints. The greatest of those is the maximum. Now, on a given interval, the function may not have any critical numbers, but f will still have extrema as long as f is continuous and the interval is closed. Our first theorem said so, didn't it? It says if f is continuous on a closed interval, then it has a maximum and a minimum. So as long as it's a continuous function and a closed interval, we will have a maximum and a minimum, even if there aren't any critical numbers. So extrema occur at endpoints of the closed interval or at critical numbers. It's taken us, what, 30 minutes to get there. That's what we got to know. Extrema occur at endpoints of the closed interval or at critical numbers. Questions? Took us 26 minutes to get there. Okay. We ready to move on? Not quite. Okay. Turn to page 169, and let's start with number 2. In exercises 1 and 2, decide whether each labeled point is an absolute maximum or minimum, a relative maximum or minimum, or neither. Since they've given us the graph, we can just do this by inspecting the graph. Okay? So don't turn this into a difficult problem. This is one where they expect you to examine the graph and decide by the definitions of max and min what you have. So, point A, down here. Max, min, yeah, it's a minimum, and it is the smallest y-coordinate on that entire graph, isn't it? Because it's filled in. Yep. So this is an absolute minimum. And just write min. Just get in the habit of putting min. Okay? Not that min. All right, point B. What do you got? Now let's see if it's absolute or not. Oops. I'm stretching a horizontal line across there. So it's not the absolute maximum, is it? Okay? So it is the relative max. All right? I'm sorry, Max. Point C, maximum or minimum? Yeah, that'd be a big neither. D, relative min. Point E, relative max. Bless you. Point E, or excuse me, F, relative min, and G, I can't even really say point G, can I? the place where point G would be if it existed, if point G existed, it would be the absolute max. Does point G exist? So it is
No.
neither. Charlie.
So relative a relative maximum. Yeah. What is on the other side of the point lower?
Right. Right. Because see, here, think of it this way, I think. B is the highest point on that little interval that I just highlighted. So it's relative because in the other part of the graph, there are some higher. So that's why it has to stay relative. And like we finally figured out after I read through enough, to be relative, like you pointed out, there's got to be someone either on each side of it. It can't be an endpoint. Okay? So, like that then would be a relative min because there's some smaller ones down here. Make sense? Yeah. If G was like right here, we'd say neither. Because it's not the absolute, and we can't call it relative because relative was defined for us. Where is it? On an open interval. Okay? All right, we good with 2?
Look that like that. If you have to get down,
Correct. Number 6. It says find the value of the derivative if it exists at each indicated extremum. So for number 6, they give us f of x equals negative 3x times the square root of x plus 1, and they want us to find the value of the derivative at this point, okay? Because that's a relative maximum. So at each indicated extremum, the extremum is singular for extrema, so instead of extreme values, it's extreme value, okay? So at that extreme value, they want to know the value of the derivative. We already know what the value of the derivative is going to be, don't we? It's either going to be 0 or does not exist, and in this case, it's going to be 0. So now we just got to do the work to show that. And it does help to know what you're supposed to get, right? All right, let's find the derivative. So f of x is negative 3x times the square root of x plus 1. Think of that square root of x plus 1 as an x plus 1 in parentheses with the exponent of 1/2 on it. And let's product rule this. F prime of x equals the first function, negative 3x, times the derivative of the second function. To find the derivative of x plus 1, quantity to the 1/2, I have to use the chain rule. And I'm going to use the general power rule version of the chain rule. So that'll be the exponent of 1/2 out in front, then the u, the quantity, subtract 1 from the exponent, 1/2 minus 1 is negative 1/2, times the derivative of u, times the derivative of the quantity. The derivative of x plus 1 is 1. That's the first half of the product rule. Second half of the product rule, plus the second function, so that quantity to the 1/2, times the derivative of the first. And what's the derivative of negative 3x? Negative 3. So we have the derivative. I guess in theory we could substitute the x-coordinate negative 2/3 in right there and see what we're going to get. But we're going to simplify it. I'm going to factor out I'm not going to factor yet. I'm going to multiply and simplify. So negative 3x times 1/2 is negative 3/2 x. And then behind the plus sign, I'm going to put the negative 3 in front. So all I did was do a little simplifying, a little rearranging. Now, I hope that you can see that there's a factor of x plus 1 both in front of the minus sign and behind the minus sign. So now it comes down to, do I want to factor out a constant as well or not? And I do, and I'm not going to factor out a 3. I'm going to factor out a 3/2. And in fact, not only am I going to factor out a 3/2, I'm going to factor out a negative 3/2. So I'm going to factor out a negative 3/2, and I'm going to factor out the quantity x plus 1, and the exponent on the x plus 1, always use the smallest exponent. So use the negative 1/2, not the positive 1/2. Now, let's see what we're left with. Well, if I divide negative 3/2 by negative 3/2, I get a 1. And then if I divide x by an imaginary factor of 1 there, then I still have an x. And if I divide x plus 1 to the negative 1/2 by itself, I get a 1, don't I? So I need to write x times 1. Just what is it? All right. Now comes the trickier part. I'm going to divide negative 3 I'm going to get a positive. Negative divided by negative is positive. And how many times does 1.5 go into 3? 2. I get a positive 2. All right, and I have that quantity, x plus 1 to the positive 1/2, and I'm dividing it by x plus 1 to the negative 1/2. When you divide factors with the same base, you subtract the exponents. So it'll be that factor with that base, and the exponent's going to be 1/2 minus negative 1/2. And what is 1/2 minus negative 1/2? 1. So the new exponent is 1. Okay. Everybody with me? All right, now, keep simplifying. So look what I'm doing here. I'm going to take that negative 3/2. I'm going to put the negative out in front. The 3 is in the numerator, the 3 stays in the numerator, the 2 is in the denominator, the 2 stays in the denominator. That x plus 1 to the negative 1/2. What do you do with factors that have negative exponents on them? Move them, change the exponent to positive. Now, it's got to be a factor, right? You can't do it with terms. How do I know? Tell me, because this is important, because this helps you guys with your simplifying. How do I know that's a factor, not a term? Because it's not only is it being multiplied by the negative 3/2, it's being multiplied by the rest of my answer, isn't it? It's times the negative 3/2, it's times the rest of all that. So the way I've got it written on this line right here, I have it written as 3 factors. Negative 3/2 is a factor, x plus 1 to the negative 1/2 is a factor, and then everything in the bracket, all that combined, the x plus 2 times x plus 1 is a factor. So you got to have it factored before you can move things around like that. Maybe that will help you later on when you're trying to simplify and you know when you can move things, when you can't. Factors. Okay? Now, that factor in the bracket, I'm going to start simplifying it. I know that 2 times x plus 1 is really 2x plus 2, right? So I've got x plus 2x plus 2. Most people call that 3x plus 2. And I'm good with that. If you want to change your exponent of 1/2 to a square root sign, I mean, I guess we should, since we started with radical notation, we should end with radical notation. But, you know, we've done the heavy lifting if you get here, haven't you? Okay. What are we trying to do on this problem? We're trying to find the value of the derivative at each indicated extremum. So we found the derivative. Now find its value when x equals -2/3. So we'll put a -2/3 in for x. Now, we know because we've seen the graph. If we hadn't seen the graph, we wouldn't know if we're going to get a does not exist or a 0. We better get one or the other, all right, because the extreme values only occur at critical numbers or endpoints. But since we've seen the graph and we know we're supposed to get 0, what's going to make that fraction equal 0? If the numerator equals 0. So we know even more precisely what we're hoping will happen. And look, it does. Because in that parentheses, 3 times -2/3 is a -2. And then -2 plus 2 is 0. And then 3 times 0 is 0. So I work the denominator out, not because I actually care about the denominator, but just because I work it out. Wow, that screen's really hanging in there. There we go. Finally got rid of it. And I get 0. Questions? All right. Number 16. Find any critical numbers of the function. All right, we're running out of time, so we're going to skip the quote unquote easy part of finding the derivative. So on your paper, write down f of x equals 4x over x squared plus 1. Skip a few lines and write down what the derivative equals. It equals -4x squared plus 4 over x squared plus 1 quantity squared. So you can go back in and fill in how you find the derivative in a few minutes. Well, tonight. Okay? So write down the function, write down the answer to f prime of x. Everybody got that? Now, we're supposed to find the critical numbers. Critical numbers occur when the derivative equals 0 or the derivative does not exist. So you are going to write this 1,000,000 times. All right, that's an exaggeration. 100,000 times here in the next couple weeks. Write this down. Critical numbers occur when f prime of x equals 0 or f prime of x does not exist. And I spaced it out like that on purpose because I'm going to do my work underneath that. Critical numbers occur when f prime of x equals 0 or f prime of x does not exist. Now, our derivative is a fraction. What makes a fraction equal 0? When the numerator equals 0. So, to find when f prime of x equals 0, take your numerator and set it equal to 0. Then you'll solve it. And so x equals -1 and x equals +1 are the two critical numbers where the derivative equals 0. And again, our derivative is a fraction. When does a fraction not exist? when the denominator equals 0, because you can't divide by 0. So take the denominator and set it equal to 0 to find the critical numbers that occur because the denominator or because the derivative does not exist. And it turns out on this particular one, once you get to x squared equals -1, there's no solution to that. We are working with real numbers. Okay? So, turns out there are two critical numbers, x equals -1 and x equals 1. So go back and fill in the work on that one that I didn't do for you. Now, I had intended to do one more example, but we're out of time here. So, here's your assignment. Page 169, 1 through 12, 13 through 35 odd, 53 through 58. You can do all of these, even though I didn't get to that last example. You can, so give them all a shot.